Now we're going to talk about a case for modular architectures. We've been talking about the importance of system architecture and why it's so critical to what it is we do. And in this short module, I just want to make the case that big software is something we should be avoiding, but we can't avoid it because what we rely on software to do is becoming more and more critical and complex, which necessarily means that it's going to be big. But by big, it doesn't have to be big in the sense of monolithic big. It has to be big in terms of it does lots and lots of things. So what I'm going to talk about now is how you can accomplish big, sophisticated, complex things, but through a smart architecture can cut them into parts and raise your probability of success, drastically raise your probability of success. One question you might ask is why hasn't M&S become a mainstream part of every service member's training? You might say, well, it has, hasn't it? Well, the question I always ask is, just ask any soldier, sailor, Marine how many training applications they have on their laptop, because they all have laptops, they all have iPads or Android devices or what have you, and they don't have anything on those devices. Training is something you do at some facility. It's not something that you do elsewhere. So it's really not ubiquitous, and it's really not even close yet. We still have too few products, and if you want to ask the question why, I think it still costs too much. We're still spending way too much money on simple development. It takes too long to get products to the warfighter, and because it takes so long to get to them, we have to make them last much longer, which means they're obsolete, which means that we have the problem we've always had where every serviceman, every service member knows that any game they can buy for $40 at the GameStop is going to be infinitely better than their training systems are, and that's a problem for us. And we still deliver products that don't fit user requirements. We simply do. Now, a few assumptions that we find is that we typically assume a number of things before we acquire any training system. Here's what I think they are. We assume that this thing is going to be expensive. Nobody ever gets into an acquisition and says, oh, this is going to be cheap. This is going to be quick and dirty. We're going to knock this thing out in no time. No, they're going to be expensive. And because it's going to be expensive, we got to find lots of customers before we can make a business case. I can't just say some little niche community of, I can't just sell something to one particular type of helicopter maintenance, one particular role, and say I think I'm going to build a training system for those guys. Forget it. I'm going to have to sell it as a training system for everybody who maintains that platform, or better yet, people who maintain any platform. And you know what the problem is with that is when you start trying to make everybody happy, you make nobody happy, and that's an issue as well. And we also think that it's going to be years. I mean, our typical acquisition pipeline is in years. It's not months. So we know it's going to take a long time. We know it's going to be expensive, and we know we're going to have to involve a lot of people. Now, to convince you that this is a really bad idea, here's some real data on project failures. Now, to be fair, this is big IT stuff. This is not specific to M&S at all. But here's the gist of this: is that 2004 data suggests that as soon as you're spending more than $750,000, and how many programs do we have in DoD that are over $750,000? How about like almost all of them? Your chances of success are only 46%. You're already less than 50. You're already less than 1 in 2 programs of over $750,000 are successful. And it gets worse, of course. By the time you're spending $1 million, you're at 32%. By the time you're at $10 million, you're at 11%, and it just goes down all the way to 2% at $10 million. This is not a very pretty picture. We obviously don't know how to build big software. In case you're thinking, well, that's kind of a new phenomena because, things have just been getting more complex. I go back 6 years earlier than that, and it was just as bad. So this is the exact same data. It's actually the same group, the Standish Group, that puts out this report every year. So it's not very good. It's pretty much a fact. Big software is to be avoided. We got to drive these costs down. How do you drive things down when you know that the things we want to accomplish are hard, they're sophisticated? So I have to be able to do hard things with software, but I still have to be able to drive costs down. Well, I got an idea on how we might do that. First takeaway from this briefing is that expensive projects tend to fail. Just get it through your head. The more money you spend, the less likely you are to succeed. It's just a fact. Well, let's look at why. If you haven't already looked at it, you should probably get yourself a copy of Fred Brooks' Mythical Man Month. While very dated, 1975, I have yet to see anything to show me that it isn't still absolutely true. And what you find is there's 4 different categories of work environments that he talks about. Let's start with the most difficult one in the upper right, is the unpartitionable task. You have a task that it's so interrelated and everything's all wound together that you can't even cut it up into teams and say, hey, you guys work on that and you guys work on that. It's unpartitionable. So it doesn't matter how many people you throw at this thing. The number of months is the number of months. In fact, you're better off just having a very small team of people working together and doing everything if it's a purely unpartitionable task. Now, the best scenario is what we call a perfectly partitionable task, which is the upper left. This is one where nice modular design, and I can say, hey, you guys are going to go write some file loaders, you're going to go do that stuff, and you guys are going to do the graphics, and you're going to go do that part, and you guys are going to do the audio, and you go do that part, and you barely even have to talk to each other. We can decide on some simple mechanisms that we're going to use for making sure our stuff works together. It's perfectly partitionable. This is nice because you can keep throwing men at this, and you clearly have a point of diminishing returns, but you can drastically lower the number of months that you're going to spend doing this by putting people on the job. Now, what you then get is a partitionable task in the lower left that requires communication. So this is a situation that's very similar to the upper left, but we have to huddle every morning and kind of talk about, hey, what's that data structure look like, and there's a database, and what are those fields, and hey, are you going to be touching this before me or after me? And I want to make sure we don't have some unintended consequences. So there's some communication here that has to happen. You get less of a payback for adding people to this, so it's a worse situation, but it still is okay and livable because you can cut your time by adding people. And here's my point. Modeling and simulation ain't any of those. Almost everything we do falls into the thing that Fred Brooks says is most common anyway in software development, which is tasked with complex interrelationships. There's all sorts of unintended consequences, all sorts of landmines you can step on, and what happens here is not only do you not get a lowering in development time by adding people, you get a raising of development time as you add people. So his quote is, add developers to a late project and you make it later. So you don't want to do this. You don't want to do this. You should get it through your head that most of what we do falls into this category. So we have complex interrelationships and we got to figure out how to deal with it. So our second takeaway is that projects with very large numbers of developers tend to fail. And very large number of developers is typically where all your money is going to go, so really 1 and 2 are almost saying the exact same thing. Now we get to really the point of this briefing, is that the problem with big software is really captured here. It's subtle, but follow this logic. Creeping user requirements will grow at an average rate of 1% per month over the entire development schedule. Keeping in mind that most of the programs that we run multiple months, maybe years, that's a lot of change. And 1% that's a pretty conservative number. So we can model this as the equation at the bottom, where R is requirements, FP is function points. Function points could be considered like the public methods in a class or something like that. They're the entry points where pieces of software touch other pieces of software. And the 1% is captured by that number, the 0.01. So now what I'm going to do in the next slide is I'm going to graph this out by manipulating function points and the percentage of the rate of change, so we can see how those two things relate to each other. Now here's that graph. So now I've got the percent of change in requirement. So there's the 1 would be 1.01, 2 would be 1.02, etc. And then I just change function points, and you can graph this out, and this is what it looks like. And what this tells you is this, is that the green area is what we call feasible, and the red area is impossible to build. Why is it impossible to build? It's impossible to build because the rate of change exceeds the rate at which you are completing the work. So it's like you're running a race and the finish line is moving away from you faster than you are running towards it. So it's impossible. You'll never get there. So it's important to manage your software projects so that they stay in the green and stay out of the red. But as we pointed out, we're terrible at this. We drift into the red zone all the time. So what are some strategies? What can you do differently? Well, here's the point. And what I've done here is I've taken the same data and turned it sideways. So now function points are on the bottom. The cost to complete is on the vertical. So the graph looks a little different. But I'm doing this because I want to show how the cost of building a piece of software of size X costs K. And I can do this anywhere along the line. So I can do a smaller version. I can say a system of size Y costs J. So now what I can do, if you follow the orange dotted line, is I can take that system of size Y that costs J, and I can build another one, and I can build another one, and I can build another one, and 4J is still less than K. I can build 4 of the smaller systems for less money than it costs you to build your big X. And as we learned before, the probability of success it increases astronomically the smaller the system gets. So I have a higher probability of success, and I'm saving money by cutting it into 4 independent parts. So the sum of the cost of J of all my J's is less than the cost of K. That's the key. So trying to figure out how big Y should actually be, you need to be able to, first of all, look at the size of your software project, and then cut it into small enough pieces so that you stay below this slope of 1. That's where the orange line is, the slope of 1. If you stay below it, you're in a feasible range. You go above it, you are drifting into the non-feasible range. So what you want to do is take anything that's above that size and cut it into independent parts using an architecture that allows you to build components of the system independent of the other components, such that the components are in the feasible range and in the cost-effective range. And our takeaways here are that large projects with many function points tend to fail, and projects with rapidly changing requirements tend to fail. So you want to get smaller, fewer function points, and you want to limit the requirements from changing. You can't really limit the requirements from changing because that's just the nature of the world we live in, other than to cut the production time. The shorter the period of time you're in production, the less time there is for the requirements to shift. So you want to cut these things. You win by making everything small. So you could already tell where I was headed with this. You need to make big systems out of small ones, and that requires architecture, and that requires figuring out how you can separate functionality into independent parts and independently build them. This keeps your costs low, the life cycle can be shorter, there's less requirement shift, your costs are low, so you can execute, and you're in the range when your likelihood of success is far greater than it would be if you let it get big. So you need to be okay with small, cheap training systems that you replace in a few years. You need to stay away from those big, sophisticated things. Do things smaller. Stop doing things so large. And lower cost implies smaller development teams. You're going to have a lot more small business involved in this. You're probably going to have less functionality. You might maybe targeted training, part task training for targeted user groups. You're going to have less time for requirement shift. We already talked about that. You can probably get away with having a smaller customer base than you could have otherwise, and you might actually have greater interaction with your customer because you're going to have it's going to be a very targeted product. So that's the gist of this, is that I just wanted to make the case of yeah, it's great to talk about big picture architecture and why it's a good thing, but actually look at some real data and make a very compelling case for why you want to stay away from big software implementations and head towards smaller implementations that are with interoperable parts that maybe target smaller user groups so that you can be more specific about what you're doing, but probably cut the features down, cut the costs down. When you see big software projects that are planned over multiple years and maybe multiple millions of dollars, you should start to get worried right away. I think I've given you enough data to convince you that there's at least enough danger there that you'd want to avoid it if you possibly could. But it takes some vision and it takes some idea of how you would get around that in order to pull that off.